we're going to look now at kind of differentiation, I suppose, in the general sense. And specifically, we're going to start by looking at differentiating by first principles. But let's just generally look at what we mean by differentiation. So differentiation is used to find what we call the rate of change of a function. So the rate of change. And we usually say the rate of change with respect to. So you'll see this a lot with respect to a particular variable. So a lot of the time, I suppose generally it's going to be the rate of change of f of x, my function, with respect to x, which x is the variable in question. So we're saying maybe, how does my function change as x changes? Or how does my value of y change as my value of x changes over my function? Okay, so kind of looking at kind of how does one thing change with respect to another thing. And we've two ways of denoting our derivative. So one of them is if we have f of x, we might denote it in this way as kind of this f dash x or f prime x. And the other way then is to write it as dy dx. And here the d part actually means kind of change. It comes from the letter delta there, the kind of triangle. So delta means change, Greek letter, it means change, and it would kind of have taken that from delta into just saying d. So dy dx, we're saying change in y over change in x. And we've kind of seen, or we kind of should get this idea that the derivative is related to the slope. So slope of a function, if you think back to your coordinate geometry, was y2 minus y1 over x2 minus x1. So change in y over change in x. And the derivative of a function, we say, is the slope of the tangent to the curve. So if I drew in a tangent to the curve at a particular point, I could use the derivative to find the slope of that tangent. And for a curve, the value of the slope depends on the value of x. So we can kind of see that a little bit here. So let me see, I know it's saying maximum, we'll zoom in a bit more. So we can kind of see here that depending on where I am on this function, this quadratic function, depending on where you draw this tangent, you're going to get a different slope. You're going to get a different value for my slope at different points. And we can kind of see there, say at the bottom, that the slope is just going to be 0 because my tangent is just horizontal. Then on some sides, my slope is positive, or my tangent looks to be positive. On the other side, my tangent looks to be going negatively or have a negative slope. So it depends where I take, or what my value of x is, or kind of dictates what the slope is going to be and what the derivative is going to be at those particular points. And that's going to come up a lot later, that when we find the derivative, that derivative a lot of the time will still depend on x. It will still have x involved because, as we see here, the value will change depending on what x is. So we look here at first principles. Now, first principles is quite important, and it's really where a lot of this differentiation kind of comes from and how we build up to the general rules that we'll be using kind of more frequently. But it's important that you're able to use first principles, and there's a bit of kind of theory or idea to kind of look at here that kind of helps us remember or really understand where the derivative comes from, where all those parts come from. So we've said here the rate of change, or the slope at a particular point, is the slope of the tangent to the curve at that point. So the slope of our function is kind of the slope of the tangent to the curve. And if we wanted to properly calculate this value, what we could do is we could take a particular point. So say we put a point on our graph here. We'll call this point A. It has a value of x, it has an input of x, and that means that my function then at that point, if I evaluate that, I get f of x. So we don't know what the function is, it doesn't particularly matter, we're working kind of just in general terms here. So when my input is x, I get out f of x. That's just your general understanding of a function. And what we're going to do is we're going to name another point as well. And this point is going to be h away from the original point. Okay, h is some number, so it could be 2, it could be 7, it could be whatever you want. So we're going to say that the first point was here, at x is x, and my next point is going to be x plus h. It's going to be h across from that. So my point B has an x value of x plus h, and it has a y value of f of x plus h, so whatever the value of my function is at that point. And if I wanted now to work out the slope of this particular line, of this line that I have here, my tangent line, well, what I could do, or the chord, I suppose, not even a tangent, the chord between these 2 points, between A and B. So let's even just keep it simpler. We'll just connect those two. So say the chord from here to here. If I wanted to get the slope of that, I could use my rise over run, or I could use my slope formula. It doesn't really matter. If we look at the rise over run, for example, here, we can see that I've gone up a distance of f of x plus h minus f of x. So that's my y2 minus y1, or my rise. And my run is I've gone h across. We can see in the bottom here, we're using this idea that we have from coordinate geometry. Y2 minus y1 over x2 minus x1, or rise over run. These were all our ways of finding slope previously. Now we're adding in an extra way. But this would give me the value of the slope of this chord that I've marked in green there from A to B, and I get f of x plus h minus f of x over h. That's the slope of the chord from A to B. Okay. Now, what we could say, and we look over here, we have a little GeoGebra file, so let's have a look if it loads. There we go. So if we're looking at this same idea that we have here, so I have my 2 points. I have my 2 points here. I have 1 point we can see up the top. Is this going to load for me? Might have to do with it. There we go. So I have 1 point up the top here. So say down, say, I don't think I can draw on this, no. So down, if we look at this point P here, that point P kind of lines up with my value A that I had in my diagram there, and we have another point up the top of Q here, this one here, and that kind of lines up with what we had for B. So it's a different point, it's a particular distance away. Okay, in this case, they've said that this distance is maybe 2. So we can see here that one of the points x is equal to 1, zoom in a little bit. At one of the points here, x is equal to 1, and at the other point, x is equal to 3. So we can see the difference there. So what happens here then is if I make this distance between them smaller, so noting here, let me see how far I can draw up, noting here that this distance is my value of h, okay, this distance at the bottom, this pn, is h, as we were saying in the other case. So if I make this distance smaller and smaller, my point Q there is getting closer and closer to what P is. Okay, and we can see what's happening as well to my dotted blue line. That's my chord that I have, that I've created between those 2 points. And what I would like is, if I'm calculating this slope between P and Q, I would like that to give me the slope of my function, not this line. I would like the slope of the function at this point P. And that slope has been drawn in for us in red there, but I want to be able to calculate that myself without just having to obviously take the answer I'm given. So if I continue making this distance between these 2 points smaller and smaller and smaller, if I make it smaller and smaller and smaller and smaller, we can see that that dotted blue line is just getting closer and closer to my red line. And if I make it as small as possible, so that my point Q is essentially on top of P, then my blue dotted line ends up being right on top of my red line there, the tangent line. And we should hopefully be drawing some connections or comparisons between this idea and this phrasing that I'm using here. So if I make the distance smaller, if I make that distance go closer and closer to 0, then my tangent line there will actually end up being, or my dotted line ends up actually being the same value as that tangent line. Okay, so what we do, or how we relate that to maths, and hopefully we kind of are getting that idea, is we take a limit. So as we said, as h gets smaller, the slope of my chord, the slope of that line from A to B, gets closer and closer to being the slope of the tangent at A. So in order to relate that, or to write that in maths terms, we write it as the limit as h goes to 0, where h is that distance between A and B. As that gets closer to 0, I will get my slope of my function. And that is kind of the key for differentiating from first principles. So if I have a function f of x, and if I want to get the derivative from first principles, I need to first calculate f of x plus h. Okay, so at some point that's a bit h further from the original point x, And then I need to evaluate this limit as h goes to 0 of this expression. Now this is an expression that you need to know off. You need to have learned this off. It's a very important expression. It's very important that you're able to do this from first principles. It's very important that you kind of have that skill, because if you're asked to do it, you won't be able to just use the other rules that we're going to be looking at. You have to show that you know how to evaluate from first principles. So let's have a look at how this works with some examples here. So we know we have our formula or a rule. We'll just leave it up the top there for as long as we can. So to use this rule, I need to have f of x plus h. Everything else is kind of given to me in the question. So if this is my function f of x, this is my function f of x. If I want to find f of x plus h, that's going to mean that I put in x plus h anywhere that I see x. So I'm inputting x plus h into my function. So that's going to be 3 times x plus h plus 7, which gives me 3x plus 3h plus 7. Let's just evaluate now the top part of the fraction. So the top part of the fraction was f of x plus h minus f of x. So f of x plus h is 3x plus 3h plus 7 minus 3x minus 7. Okay, so my f of x plus h here, and my f of x coming from the question then. I'm making both parts negative because I'm subtracting by that function. And that's going to just leave me with my 3h. So now to get my derivative, it's the limit as h goes to 0 of f of x plus h minus f of x all over h. We've already evaluated the top part there, so it's the limit as h goes to 0 of 3h over h, which is going to be the limit as h goes to 0 of just 3. And for that expression, there is no h value, so as h goes to 0, that's just going to stay as 3. That's just going to stay as 3. Looking at my second example here, so a little bit more involved in this case, let's start the same way again by finding f of x plus h. So I'm just going to sub that in for everywhere that I see x here. So I have a quadratic, so I have some squared terms to just watch out for here. X plus h plus 7. So let's just get ready to evaluate. So x squared plus 2hx plus h squared minus f of x minus, 4x minus 4h plus 7. Let's just multiply this all out then, because we've seen already that we can end up eliminating some of these terms when we subtract the original function. So it's just important to kind of lay it all out appropriately. So let's evaluate f of x plus h minus f of x. Okay, so 3x squared minus or plus 6hx plus 3h squared minus 4x minus 4h plus 7 minus, and I'm subtracting this whole function, and I'm going to just lay it out very explicitly this time so that we can really make sure we're getting all the points. 6hx plus 3h squared minus 4x minus 4h plus 7 minus 3x squared plus 4x minus 7. Okay, and then just accounting for any terms there that would be subtracted or that will kind of be eliminated, plus my 3h squared, my 4x and the plus 4x, 3x squared and the minus 3x squared, and the 7 there. So we just end up with this expression here. Now I'm taking the limit as h goes to 0 of f of x plus h minus f of x all over h. So it's the limit as h goes to 0 of, well, we've already evaluated the top part there because that was what we had highlighted in yellow, all over h. What we can do is we can divide that h on the bottom into the terms on the top if it does divide, and it does divide into all three there. So I get 6x plus 3h minus 4. I can then evaluate my limit, so 6x plus 3 times 0 minus 4, so just subbing in 0 for h, and I get 6x plus 4, as my derivative. And we can see that the derivative there depends on what x is. So for different values of x, I would end up with a different value of my derivative there. It's just watching out for those different parts. So we have some more examples here. So differentiating from first principles, find from first principles the slope of the tangent to the curve, which has equation f of x equals x squared minus 2x plus 5 at the point where x equals minus 1. So we've one additional step to kind of follow through here. Otherwise, everything else is still the same. So let's give it a go. Let's start it the same way as we've done the previous two. We're going to start by finding f of x plus h. So subbing in f of x plus h gives me x plus h squared minus 2 times x plus h plus 5. So let's finish this out. So x squared plus 2hx plus h squared minus 2x minus 2h plus 5. And I can't really simplify that down any further for myself. So now we're going to look at getting f of x plus h minus f of x. So this will be the top part of our fraction. So we take our answer from the first part there, and we're going to subtract the original function. Okay, adjusting the signs as we go. So I'm left with my 2hx plus h squared minus 2h. Then again, we get the limit as h goes to 0 of this top part. Now, this was the top part of my fraction, so let's just sub it in. All over h. I can divide the h there into the top parts, and it leaves me with 2x plus h minus 2. And then evaluating my limit gives me 2x minus 0 plus 2, which is of course just 2x plus 2. Or sorry, minus 2. There we go. Change my signs. Yeah, 2x minus 2. So we've evaluated now my derivative. So that's my derivative. So dy dx, or f dash x, whichever you want to use, is 2x minus 2. And we want to find the value of that when x equals minus 1. So remembering that our derivative is the slope of the tangent. Okay, my derivative is the slope of the tangent to the curve. So when x equals minus 1, I can sub that in to this kind of slope formula, if you like. So minus 2 gives me a value of minus 4. So when x is minus 1, the value of my slope then is going to be minus 4. Okay, so first principles has come up, I suppose, a few times. I've put a few examples into the notes or into your questions for you there. So we have an example here from 2022, there's an example from 2020, and there is an exam question from 2017 also. So we have 3 exam questions for you to practice with. We probably want to do all 3 because again it ends up being the same processes and the same ideas each time that you're really following through. So we'll maybe just look at one of these exam questions here. If we look at the 2020 example, okay, if we look at the 2020 example here, so approaching this question, we can see it looks a little bit different. We've been asked to do it by first principles. So the first thing we need to do actually is multiply out this bracket. So multiplying out this bracket gives me 6x squared plus 12x minus 10x minus 20, which simplifies down to, of course, 6x squared plus 2x minus 20. Okay, it's really important that we multiply that out first. Now we need to go as before, and we're going to evaluate f of x plus h, because I'm remembering that my rule here that I'm going to be using is the limit as h goes to infinity of f of x plus h minus f of x over h. So evaluating f of x plus h here, it's 6 times x plus h squared plus 2 times x plus h minus 20. Multiplying out 6 times x squared plus 2hx plus h squared plus 2x plus 2h minus 20, and just continuing as before to multiply out fully. Okay, good. Okay, let's go then with getting the top part of my fraction here, which is of course my f of x plus h minus f of x. So we're taking that full expression from the first part, and we're going to subtract that multiplied out fraction that we had there, that multiplied out expression. So let's just really lay things out for ourselves here to be careful with our signs. I'm just going to use a bracket first of all, so I'm subtracting everything that's in that bracket. I'm going to then just rewrite all of this out. So 6x squared plus 12hx, quite a long expression here, plus 6h squared plus 2x plus 2h minus 20 minus 6x squared minus 2x plus 20. Okay, so simplifying all that down, accounting for any terms that kind of will, I suppose, cancel each other out. We have that term there. We have my 2x and my minus 2x, and I also have my minus 20 and my plus 20 here. So what I'm left with is the 12hx plus 6h squared plus 2h. Okay, so that's going to be the top of my fraction. We can write out then, if I was doing this in an exam, I would write out my general rule. So the limit as h goes to 0 of f of x plus h minus f of x over h. Then I'm going to sub in what I have for the top part here, which is what we've highlighted in yellow. So it's the limit. We need to keep writing limit until we evaluate the limit. Okay, I can divide by h, or I can divide that h into the top terms there. So I get 12x plus 6h plus 2. I can evaluate my limit then, so 12x plus 6 times 0 plus 2, and I get a value of 12x plus 2. Okay, very important to note there that we have to do it by first principles. So we're going to look at another rule that would kind of save us some time there, but in fact you got no marks for doing it that way. So you had to do it by first principles. So it's very important that you know this process thoroughly. Okay, the same thing applies in the other two exam questions we have there. You're following through the ideas. We have the solutions, or we can find the solutions online either way. But with first principles, the main thing is to be aware of that kind of formula here, this idea. So you need to know this formula, and you need to know that off. Okay, you really need to know that idea off. So to find it by first principles, you have to use this idea. It has to be the x plus h idea that you're making use of in order to evaluate by first principles. So limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so very important that you know that off. Once you know that off, it's just about taking kind of step by step, following it through, making sure that you're evaluating everything right, that you're ending up with those terms that have h's in them. You should end up with all terms that have got h's in them, so that some of them can be eliminated. And then when you apply the limits, that you end up kind of with a term or two again being eliminated, and you end up with your overall derivative.